So go ahead. Many thanks for being here and agreeing to be part of the school. And
easy. Thank you.
yeah.
Okay. Yes. So I'm Steve. I've been working in electromagnetic methods for about 40 years now, which makes me older than all of you. And I specialize in marine methods. Scripps is a famous marine institution. But I've dabbled in universe theory and mineral physics, rebirth induction, which I think makes me sort of very, very IAGA. I actually taught this summer school for in its second time in Prague about 4 schools ago. I have EM induction is a big topic. I have way too much stuff, but you can all get access to it. You should have all been able to get access to it already. And the idea here is to try and tell you what it's all about. There's a lot of math, but we can gloss over it. And once you know what's there, with the slide deck and the notes that I distributed, if you need to go back and want to learn it more carefully, then you can do that. So the idea here is to give you a big picture. There's lots of detail on the slides, but it's not going to pick it all up in one day, but at least it'll be there. So here's the plan. Start out with some introduction and some of the history of the method. Talk about Earth's electromagnetic environment. You should have seen some of this already with the magnetospheric work. The electrical conductivity of rocks and minerals. Why does the Earth conduct electricity in the first place? Some theory, instruments, and I cover a little bit of observatory instruments, so you should have seen some of that already as well. Magnetotelluric data processing, geomagnetic depth sounding. Magnetotelluric method is good for the top part of the mantle. Geomagnetic depth sounding can in principle go all the way to the Earth's core. One-dimensional forward modeling, two-dimensional and three-dimensional forward modeling, inverse modeling, and then when you're all exhausted at around 4 o'clock after the break, a colleague of mine, Oliver Ritter, who works at Potsdam, will come out and we will walk over, and he operates a magnetotelluric instrument facility out of the observatory, and we'll get to look at some instruments and calibration facilities and listen to Oliver to give you some relief. So, has anybody shown me this? No. This is why we're here. So, there's a thing called ICSU, the International Council of Science Organizations Unions, and there are 32 different unions. We're part of the IUGG, the International Union of Geodesy and Geophysics. And under IUGG, there's geodesy, seismology, volcanology, and we are IAGA, Institute of Astronomy and Geomagnetism. And under IAGA, there are 6 divisions, which are all being represented to some extent by this short course. And I'm in Division 6. It's a relatively new division. It used to be a working group under Division 3, I think it was. But we became so big that we were able to become our own division. So this is what we're talking about today. Electromagnetic induction in Earth and planetary bodies, and induction, electrical properties, surveys, planetary materials. Some background material. I wrote a chapter for this thing called the Treatise on Geophysics, which is sort of today's lecture in one chapter, and that's available online. There are two books on the magnetotelluric method. One edited by Alan Jones and Alan Shave, has a whole bunch of chapters written by various people. And then there's a little lighter book, Practical Magnetotellurics by Fiona Simpson and Custom Park. And then there's a website if we have time, we'll play around with using some of their online tools today. This is Niemegk, run out of Vancouver, a group of people in Vancouver that have Doug Oldenburg's SEG short course on this website, and a whole bunch of interactive tools for doing electromagnetic modeling. It's a work in progress, but the 1D module is up and running, and we might have a chance to play with this. This is targeted at a sort of Society of Exploration Geophysics, SEG level. It's less deep earth and more resource and environmental exploration. You can see unexploded ordnance is one of the things that methods are sometimes used for. So why do we care about EM induction? It's a wonderful way of looking at geology that's hidden beneath the surface of the Earth. So here's some relatively new results that come from the US array. There's a large project in progress in the US to cover the entire continental US with magnetotelluric measurements, long-period magnetotelluric measurements of a spacing of about 70 kilometers. And it started on the west side, and here are some 3D inversions of the data being collected. So this is the northwest of the USA. These are depth slices going down from 100 and some kilometers to 300 and some kilometers in the Earth. And then these are two sections across the model. This is the wonderful plate subducting between North America. This is the Wyoming Craton. Normally, in electromagnetic methods, blue colors mean resistive, that is cold, dry, hard rock, and warm colors means conductive, which would be hot or wet or sedimentary regions. This is not universally true. The hydrologists like to do things the other way around. The exploration community like to do things the other way around. So you always have to look at the color scale to see which way around it's going. This is from Australia. The OzLab program in Australia is doing something similar to the US array, where they're covering all of Australia at 50 kilometer spacing. And here's, again, this is a work in progress, but here are some results from the northern part of the country, and this is a depth slice at 36 kilometers. And the geology has been written on here, and you can see that the electrical conductivity structure follows the geology. You've got this thing called the Wirrawurra Suchi here, which is reflected in conductive rocks. Mount Isa is a mining district. You can see that that's associated with the conductive rocks as well. And so this provides a way of looking into the Earth to study geology. Here's some of my own work. This is the mid-ocean ridge at the East Pacific Rise, where the mantle is upwelling to melt and erupt and form oceanic crust, and you can see molten mantle in this wedge, tent shape upwelling here. So the mantle's upwelling broadly and then focusing at the mid-ocean ridge to form the ocean crust. This is groundwater off San Diego, and because it's hydrology, they They've inverted the scale, so the red colors here are resistive fresh water. And what we see is that the water is fault bounded here off San Diego. This is a subduction zone off Nicaragua, where you can see the red conductive sediments being subducted. You can see as the slab bends and breaks and water goes down these faults, you can see the water down in the cracks here. Something interesting is going on in the prism here. And then this is off New Zealand. This is gas hydrate, which is this really weird stuff. It's a whole other story in itself. And this is overlaid on seismic reflectivity. This ESR is the boundary between free gas and solid gas hydrate. And you can see this gas hydrate fingering up into the. So these are lovely pictures that tell you something really meaningful in terms of geology. And the electrical conductivity signal that we're looking at is huge compared with something like seismic velocity. So in common earth materials, we're spanning already 5 orders of magnitude here from seawater and basaltic melt at around a few Siemens per meter or a fraction of an ohm meter. We'll talk about what that means a little later. And then as things get dry and cold, they get more resistive. And you see fresh water is more resistive than seawater and so on. So we've got lots to go on. So the electrical methods menagerie, there's a lot of stuff you can do with electrical conductivity. There's DC resistivity, which is a relatively shallow but useful and fairly simple to use method where you pass DC electric current through the ground. Use a lot for groundwater. Self-potential, where you actually look at voltages at the surface of the earth, which is created by water flow and chemical reactions in mineral deposits. Induced polarization, where you charge the ground up with electric current and then switch it off and see how charge is being stored in the ground. That's very useful for mining. And then the inductive methods, magnetotelluric method, geomagnetic depth sounding, a little bit on controlled source. That's what we're going to cover today. And then at the other end, there's ground penetrating radar, where the frequencies are high enough, you actually get wave propagation in the top few meters of the Earth. So we're going to be mainly concentrating around here. So the magnetotelluric method, we've been talking a lot about this. The way it works is the Earth creates a time-varying magnetic field. You know about this already. It comes down from the magnetosphere and ionosphere. It's mainly associated with the interaction with the solar wind. And that we measure that magnetic field at the surface of the Earth in 2 or 3 components. And it induces electric currents in the ground, which we measure with electrodes and voltmeters. It's a free source of energy that we can use here. It's relatively simple to collect data, less simple to process it and interpret it. We'll find that out soon. We can supplement that source of energy with our own man-made transmitters, either magnetic fields with loops of wire or electric fields with grounded electrodes putting currents to the ground. And you can see it, you use the same set of receivers to make the measurements. And that's called the controlled source method. And it's useful for slightly shallower investigations in the magnetotelluric method. Controlled source methods can go down a few kilometers at the most. The magnetotelluric method can go down, as you've seen, several hundred kilometers. So what is EM induction? Here's an introduction. Here's a start. So let's say you've got a transmitter coil for a man-made source of controlled source of energy. You put a current through a coil of wire and it creates this magnetic dipole, but it's varying in time, some frequency, or you switch it on and switch it off. And the time-varying magnetic fields will induce electric currents in conductors. So let's say this is a conductive ore body. you push a magnetic field across it, you wobble the magnetic field, and that creates an electric field, which drives electric currents if it's conductive. And then these electric currents create another magnetic field. So we call this the primary magnetic field. The electric currents drive a secondary magnetic field in the ground. And that secondary field is different from the primary field in three ways. It's in a different direction. This orientation is different from this orientation. So these secondary fields are not in the same direction as the primary fields. They're a different size. They're a lot smaller than the primary field. And they're also a different phase. They're out of phase with the transmitted signal. So if you measure any of these things, the direction, the size, or the phase, you can learn something about the underground conductivity structure. And there are methods that do all of these in different ways. So the workflow, you start out by measuring these magnetic and electric fields at the surface of the Earth, the magnetotellurics. If you're doing controlled source EM, you're measuring the amplitude and phase at a single frequency typically. And you take these time series measurements and you move them into the frequency domain. So in the magnetotelluric method, you end up with this sort of amplitude and phase as a function of period or frequency. Or in CSEM, you get these amplitude and phases as a function of position, distance away from your transmitter. And then you take these data, these are the things you measure, these are what we normally call EM data, and then you use this method called inversion to turn these data into a conductivity picture of the sort that I've been showing you. But that's just electrical conductivity. What does that mean in terms of geology and physics of the Earth? Well, then you need laboratory measurements that relate electrical conductivity to other things like water content or temperature or melt content or chemistry. And then from that, you can infer things like melt fraction, water salinity, temperature, gas hydrate fraction, if that's what you're interested in. So this is the sort of workflow, and I'm going to be talking about the whole workflow today. From collecting the data to processing the data to inversion and some laboratory stuff. That's why it's a complicated subject. So, just start with some terminology. We'll be talking about electrical conductivity. That's normally sigma. The units are Siemens per meter, and they're just the reciprocal of resistivity. And it's a measure of how well electric charges pass through a material. Rho is electrical resistivity. Its units are ohmmeters. It's just the reciprocal of conductivity. Magnetic field is B. It's measured in Teslas, but the Tesla is a big magnetic field. And for geophysics, most people use nanotesla, 10 to the minus 9 Teslas. B is sometimes called magnetic flux density. And then there's this thing called H, which I call the magnetizing field. It has a units of amperes per meter. It's basically a mathematical construct. You can't measure it, but people like it all the same. And to make things really confusing, a lot of people will call that the magnetic field too. We'll talk about the difference that the B and H are related through this thing called magnetic permeability, and that's a measure of how well rocks magnetize. And I'm sure Gillian's told you all about how you get magnetization in rocks, right? So yeah. E is the electric field. It's just units of volts per meter, and it's basically the field created by electric charges. J is electric current density. It's in amperes per square meter. That's a flow of charge through material. It's a little like current in a wire, except we don't have wires, we have big blocks of rock. And so instead of measuring current, instead of just measuring amps in a wire, we have to measure current density. Mu is a property of materials, but it also has a value for free space. It's almost exactly 4 pi by 10 to the minus 7 henries per meter. It used to be exactly 4 pi by 10 to the minus 7, but then we went and redefined the kilogram. the grand kilo in France was usurped, and the kilogram was defined in terms of other physical constants, and that meant that mu changed just a little bit before pi by 10 to the 7. Epsilon is electric impermittivity. It's how a charge polarizes in a material with an electric field. We're not going to worry about epsilon, but I'm using it here for completeness. And it has a free space value as well. And do interrupt. If I run out of time, it's my problem. So if you don't understand something or you want to say something, do chime up. Okay. So that's just the setting the stage. A little history. Have you seen this? Yeah, some of it. This is the famous experiment by William Gilbert in the 1600s, where he took a spherical piece of lodestone or magnetite, and then took these little slivers of iron, and he showed that they all had an orientation around the sphere of lodestone that was similar to the direction of the magnetic field on the Earth. So that's a really famous picture. And it's the picture on a award that the American Geophysical Union, Geomagnetism, Paleomagnetism, and Electromagnetism Society uses the Gilbert Award. But it turns out that Gilbert, if you look in chapter 2 of book 2, he talks about electroscopes and rubbing amber to create an electric charge. And he invented the word electric. So he's not only famous for magnetism in the Earth, he's also famous for introducing electricity. Then following on, we have the classic development of electromagnetic methods. Coulomb looked at the force laws on he worked out the inverse square law of forces on charges. Volta invented the battery, so people could start creating electric currents in the lab to play around. Gauss, Carl Friedrich Gauss from Göttingen in Germany, is a big name in all sorts of things, and one of the things he did was create a flux theorem out of Coulomb's law. Ørsted observed that an electric current in a wire reflected a compass needle, a magnet. And then Ampere came along and quantified Ørsted's observations, and you noticed that one wire with a current had a force on another wire with a current. So he worked out that if you coiled the wire around and put a current through it, you could create a dipole that looked a little bit like a lodestone magnet. Michael Faraday made a current by moving a magnet across a conductor. He in fact predicted that water flowing through Earth's magnetic field would create an electric field, and it was 80 years before people actually measured that in the Thames. And then the big name is Maxwell, James Clerk Maxwell from Edinburgh. He recognized that Ampere's law and Faraday's law were related, and he fiddled with the equations to create light, electromagnetic radiation in the vacuum, and that was a big thing. But what I like to remind people of is that what you understand as Maxwell's equations are, in fact, Oliver Heaviside equations. So from a geophysics point of view in the history, people started, when people created telegraph wires, they started stringing these electrical wires across the ground to carry conversation signals. They noticed that magnetic storms created electric fields in these wires. And so here's a very early picture of the signal in telegraph wires during a magnetic storm. Gauss again then developed the mathematics to take these magnetic field variations and work out whether they came from outside of the Earth or inside of the Earth. And it's not obvious that you just heard all about magnetospheric physics, that's natural for you to understand that the magnetic field variations come from outside Earth. But in the beginning, they were just field variations. They could come from anywhere. And then in 1859, Planet noted that the aurora were related to these disruptions in telegraph light. The Greenwich Observatory started actually measuring Earth potentials as well as magnetic fields. And then Schuster, towards the end of the 1800s, Schuster basically worked out that these variations in magnetic fields were creating electric currents in the ground, and that was the big deal from a geophysics point of view. And so by the early 1900s, the relationship between magnetic field variations and Earth currents was becoming well understood. The people started to try and model this. And the first people to do this, Sidney Chapman noted that the daily variation of the magnetic field was consistent with a conductor inside the Earth that wasn't actually at the Earth's surface, but smaller than the Earth. And then Lahiri and Price created this exponential model, simple 1 or 2 parameter model for the magnetic field variations down to about 1,000 kilometers. So what this is electrical conductivity on this axis and depth from the Earth on this axis. So this is the core mantle boundary here, and this is the upper mantle, lower mantle boundary, 670 kilometers, which is, the seismologists tell us that that's there. And then Roger Banks showed that at around 27 days, the Earth's field looked like a dipole, what we call the P10. 27 days, as you probably know, is the time it takes the sun to rotate. So if you've got a sunspot on the sun, waving the magnetic field of the Earth, then it's 27 days signal. And then Banks used this by assuming the geometry of the field, he was able to work out what the electrical conductivity looked like downward depth of about 1,500 kilometers. To try and get to the lowermost mantle, this guy McDonald basically looked at the secular variation from the Earth's core. So you've probably heard about that from the core field part of this class. Basically, he tried to work out how the electrical conductivity attenuated those variations of depth, and we produced this model. And even though these are the very first models of the deep Earth conductivity, they're not bad. This is a model I made for that treatise volume, it's been pretty good agreement. So, and the big deal is there's a big jump in conductivity between the upper mantle and the lower mantle as the minerality changes, and we'll talk about that. So another thing of note in passing is the development of DC resistivity methods. Frank Benner was working in the US Bureau of Standards measuring the electrical conductivity of materials, metals and so on. And he took the laboratory approach out in the field, and he passed a current through the ground between 2 electrodes and measured the electric field between another 2 electrodes, and that became some of the first geophysical methods to look at near Earth conductivity. And the Schlumberger brothers were doing something similar at the same time in France, also measuring salt potentials. And we'll come back to this when we talk about going back into the lab, which is where that came from. And then inductive EM, this is, as far as I can tell, this is the beginning of controlled source EM methods. This is a patent from Daphne Williams, where they were creating alternating frequency, alternating currents, and using it to try and search for ore bodies. An apparatus for detecting and localizing mineral deposits. As far as I can tell, that's the first use of controlled source EM in geophysics. The big event was magnetotelluric methods, and in the 1950s, early 1950s, Tikhonov in Russia, Rikitaki in Japan, and some colleagues developed the mathematics to say how a magnetic field varying at the surface of the Earth will reduce electric currents. So they worked out the possibility and did some of the theory. Louis Cagnard from France basically described the magnetotelluric method as a practical method. So there's a lot of argument about who invented magnetotellurics. Was it Tikhonov? Was it Rikitaki? Was it Cagnard? Well, the answer is they were all working on it, but it was Cagnard who actually made the proposal in the name. And so I sort of take magnetotelluric methods from Cagnard's paper. And then later, airborne and other ground control sources and methods were developed. So this is the magnetotelluric method. As I said before, you measure the magnetic field in 2 or 3 components. You measure the electric field in 2 directions, and you can combine them to work out how electrical conductivity works. So that's the history and introduction. Any questions on that? Okay. So now, I know you've seen it before, but it's useful to talk about the Earth's electromagnetic environment from an induction point of view. This is something that Kathy Constable and I are working on as we speak. It's something we started, I don't know, 15 years ago, and we're just trying to finish it up. It's a power spectrum of the Earth's magnetic field from reversal rates to radio frequencies. So this is the power in the field measured in nanoteslas squared per hertz. And then this is frequency going from 10 to the minus 16 to 10 to the 5th hertz, which is a sort of difficult span. So this is millions of years, sorry, billions of years, millions of years, thousands of years, 1 year, 1 day, 1 hour, 1 minute, 1 second, and 1 millisecond. So are you all sort of familiar with power spectra, what it means? We'll talk a bit more about time series analysis later. But this is basically just how big the field variations are as a function of the period of the signals. And there's a lot going on here. You've probably been looking at this from a paleomagnetic point of view. All these data are paleomagnetic data from the average reversal rate of the Earth's magnetic field to paleosecular variations and then secular variations. And all that's coming from the Earth's core. The Earth's core churns in a different way and creates different magnetic fields. It creates all these variations in the Earth's main field. But then at around 11 years, what's magic about 11 years? The solar cycle. Right? About 11 years, the sun takes over and the field comes from the outside. So you get a signal at 11 years. You get a signal at a year and 6 months that's associated with the Earth around the sun. And then you get the 27-day sun rotation plus harmonics, and then you get the daily variations that as the Earth spins around under the sun. And then you get all these magnetoscope phenomena, such as the storms and micropulsations, which you've probably heard about. And then you get this wonderful thing called the Schumann resonance, which is associated with energy trapped in the atmosphere caused by lightning. And then man takes over, and we've got all this power line noise and radio frequencies and navigation signals up at this end. So all the stuff to the left of 11 years is somebody else's problem, as far as I'm concerned. That's what my wife studies. and all the stuff to the right of the 11 years is from outside of the Earth and induce electromagnetic signals in the Earth, and that's what I use for electromagnetic induction. And you can and we have used everything from 11 years to radio frequencies to study Earth conductivity. So we've got a big spectrum to work with. You've probably seen pictures like this. The Earth's magnetic environment is sort of complicated. You've got this day side magnetopause where the sun's hammering the Earth's magnetic field. You've got the auroral cusps. You've got the ring current trapped in the magnetic field. You've got the magnetotail with field aligned currents and cross-tail currents. It's all very complicated, and I don't understand it, but you guys do. So this is my vision of the. This is the famous NASA picture where the solar. This is not to scale, of course. So the solar wind is mostly protons, and we know how dense they are, we know how fast they are. It's carrying an interplanetary magnetic field of about 5 nanoteslas. This is a nice little exercise. You can balance the kinetic energy of the solar wind particles with the energy of the Earth's magnetic field, and actually predict to first order where this bow shock is at about 8.5 Earth radii, which isn't quite right, but this is a very simple piece of math, and it's nice to look at. So you've probably seen this, right? If you have a charged particle moving in a magnetic field, you get a force in the orthogonal direction, and that means the particle is forever doomed to rotate in circles, and you can predict the frequency and radius of this circle with the particle's mass and charge and velocity and the size of the magnetic field. You've probably seen all that, right? Okay. And if there's a component of velocity parallel to the magnetic field, there's no force on the particle at all, and the particle loves to go along the magnetic field. Okay. So magnetic mirroring, have you done that? Yep. Okay. This is sort of amazing math, right? So the magnetic moment and the kinetic energy have to be conserved, and as you go along the magnetic field into the poles where the field is stronger, the spinning around the magnetic field goes up. So the kinetic energy along the magnetic field has to go down, and at some point it has to actually reverse. And so the particles get trapped in the magnetic field. And this is an actual picture from NASA's spacecraft that have been mapping the radiation belts. And so these are charged particles trapped by mirroring in the magnetic field. And the big deal here is that they saw a separation between the charged particles and this outer radiation belt. This is my signal. These charged particles running around the magnetic field are what causes a field at the Earth's surface that we can use to probe the deep Earth. Because the Earth's field falls off as 1/r cubed, as the particles are spiraling around the Earth's magnetic field, the radius of curvature is smaller in the stronger field near the Earth and larger in the weaker field further away, and so there's a net drift in a westward direction, and that causes this ring current that's thousands of amps running around the outside of the Earth, causing a magnetic field. And you've probably been told that that is measured by this index called the disturbed storm time. And this is a nice little magnetic storm in 2015. You get the sudden commencement as the solar particles hit the magnetic field and compress it, and then they get injected into the radiation belts, and they create this current which opposes the Earth's main field, and so they always go negative. So a few hundred nanoteslas is a typical magnetic storm. I read in the news this morning that there's going to be a magnetic storm and auroras on Thursday. Anybody else read that? Yeah, okay, so just, you've got to get up and Thursday and look at the sky is clear. We're at 52 degrees north here. We're not in the ideal place in terms of this magnetic dipole, but it's a rare treat to see an aurora. So these magnetic storms are tied, they're tied to the sunspot cycle. The sun's magnetic field reverses every 11 years, which creates a modulation of the sunspots and the solar activity. So this is the solar output measured by the 10.7 centimeter radio frequencies. And you can see how the solar cycle is loosely, this is DST, so these are magnetic storms. That's the big magnetic storm that wiped out Canada's power system around Quebec. And you can see this loose correlation here. So the important thing from our point of view is you get this is a nice little micropulsation from the magnetic field. It's about 1 picotesla big, and it induces an electric field in the Earth, which is what I'm going to use. And then moving down, the atmosphere is obviously resistive, 10 to the minus 14 Siemens per meter near the surface. But as you go up, the air pressure goes down, and the mean-free path of any charged particle gets longer, which means that the conductivity is essentially going up. And so by the time you get to the ionosphere, where the things are ionized, the conductivity is about as conductive as the surface of the Earth. And so the ionosphere is this conductive sheet, the Earth's surface is conductive, and the atmosphere is this resistive cavity in between. So how long does it take light to go all the way around the Earth? Calculation in your head. About an eighth of a second. And if you look at the Earth's magnetic field spectrum at 8 hertz, you get a peak. And that's called the Schumann resonance. And that's all the world's lightning creating a standing wave in the ionosphere cavity. And then these are the harmonics. And it's a lovely little phenomenon. You can measure it anywhere on Earth, at any time with a magnetometer, as long as the human-made noise, this is power line noise, isn't lightning noise. So that's called the Schumann resonance, after Schumann, who first described it, and it's a cool thing. This is an example of a single lightning strike measured at 3 places, one at an observatory in Germany, near Sorbonne, an observatory in Hollister, California, and a magnetometer that a colleague and I put out in Lamoureux in Australia for just a month. So these are recording all the time. This is a 1-month measurement. And a colleague of mine, Martin Fullercrew, was able to use these sorts of data to triangulate where the lightning strike was and create this movie, which is global lightning for a month. And it's really cool. You can see storms going up and down the west coast of the east coast of the US. You can see most of the lightning on Earth is over Africa because it's got a landmass at the equator and tropical and humid. But there's a lot of lightning over the ocean that people don't normally measure. So that's a cool little thing we did in 1998 just for fun. Nice little program like that. So, and every time you get a lightning strike, you think is Schumann resonance. We can talk about lightning a little more. It's caused by convection of charges in thunderclouds, and you basically have this system of circulating electricity in the atmosphere and the ionosphere. There's about 1,000 amps traveling from the ionosphere to the surface of the Earth across the entire globe. And so there's about 100 volts between my hands, but that's okay because the conductivity of the atmosphere is not enough to support much of a current. This vertical electric field varies over the course of one day as the lightning, as Africa goes through mid-afternoon. That's called the Carnegie curve because the ship Carnegie was the first platform, scientific platform to measure that. And then you get these things called Wilson storm currents traveling through the ionosphere and so on. So the Earth acts as a capacitor with a capacitance of about a farad. There's also a daily variation as the Earth rotates beneath the Sun. The Sun heats up the conductive ionosphere on the Sun side, and you get these tidal currents which create circulating currents which create magnetic fields. And so if you look at the Earth's magnetic field, whoa, yeah, I have to push the wrong button. Trouble with these remotes. Yeah, so you get these circulating currents which create magnetic fields. So if you look at the magnetic field of an observatory, such as Niemegk, over a period of a day, you see about a 30 to 50 nanotesla cycling of the Earth's magnetic field. So here are 3 days in a Canadian observatory. So that is the Earth's magnetic field. Yeah.
Your Schumann resonance, is that a blessing or a curse for the stuff that you do? And how many effects or harmonics do you have before it gets
That's, well, a blessing or a curse. I would say blessing. It's external energy that we use for induction. It's the source field is the entire cavity, so it's a nice source field. It's a uniform source field. It's energy in a part of the spectrum that doesn't have much energy, so it's good like that. How many harmonics you can use? You can see 7 here if you do an act of faith. This is in Clark Dry Lake, which is about 100 kilometers east of where I live. It's in the desert in Southern California. It's surrounded by mountains, which tend to shield the power noise a little bit. It's conductive, which means that the noise doesn't propagate as well. So yeah, it's a nice thing to see if you're doing any of this work. But you know, from a spectral analysis point of view, it's just so pretty. Yeah, so it's in this bit of the field where we're running out of energy. So it's nice. Okay. Other questions about the external field? I know many of you here are studying. As I say, you probably don't know about it. But it's always nice when you're talking about induction to explain where your signals are coming from. Okay. So how do rocks conduct electricity? How does anything conduct electricity?
Free charges. Free charges.
Free ions, charges, moving. Yeah, that's about it. Let's talk about that. So I showed you the middle bit of this picture before. If you extend it from common earth materials down to the mineral level, we're now looking at 20 orders of magnitude. Conductive ore minerals such as pyrrhotite and graphite, which is pure carbon, are way down on the conductive end, and quartz grains are way up on the resistive end. And yeah, you get ions. Most of the ionic conduction we talk about is basically mostly sodium and chlorine in water. Seawater, but even fresh, what we would call fresh water, has got some dissolved salt in it. Most of that salt is sodium chloride. And as you probably know, seawater conducts electricity. All water conducts electricity to some extent because of the dissolved ions. And then various rocks, crustal rocks, unless you found an ore body, crustal rocks basically conduct in proportion to the amount of water and the salinity of the water. When you get into ore minerals, you get semiconduction, and if you're lucky enough to find a chunk of silver or gold, of course, there's metallic conduction. And then when you go deep into the earth, you get this thing that warms my heart, which is conduction in silicate minerals at high temperatures, where you get crystal defects that can move charge through a crystal that would not otherwise move charge. And that's when you get down to mantle, and also molten rock. Basaltic melt is about as conductive as seawater. That's an easy thing to remember. I've got a volcano in Hawaii spewing magma. That magma conductivity is about the same conductivity as seawater. So electrical resistivity has units of ohm meters. That sort of means if you take a cubic meter of a rock and put electrodes on two sides and measure its resistance with an ohm meter, you get 1 ohm. If it's 1 ohm meter rock. If it's a 100 ohm meter rock, you get 100 ohms. Now nobody's going to build circuits with cubic meters of rock, but that's the relationship between resistivity and resistance. Resistance is ohms, resistivity is ohm meters. So if you've got a sample of a rock in the lab, you put electrodes across the ends and pass a current through it and measure the resistance R with a voltage V, measure the current I. The resistance is basically just the voltage drop divided by current. And then if you take the surface area and length, you can then back out resistivity. The resistivity goes up as the resistance goes up as the area goes up, and down as the length goes up. So yeah, you just take a rock, pass a current, measure the voltage drop. And that sort of works unless your electrodes are not making very good contact with the rock. And the problem with the two electrode method is you're measuring the contact resistance of these electrodes in series with your rock. And because you're passing current through the electrodes, you're getting a voltage drop across the electrode. So sometimes that's the only way to make the measurement. And I'll explain those circumstances in a moment. But if you've got a big sample, the better way is to put two electrodes across the middle of the rock, the 4-electrode method, and use the electrodes at the end to pass the current, but make a voltage measurement across these two electrodes. And because the voltmeter impedance is very big, your average voltmeter has an input impedance of 100 megohms. It's not drawing any current, so you don't get any voltage drop across
Okay.
these leads here, so you get a better measurement. You're only measuring a third of the resistivity of the third of the resistance of the rock, but that's enough. And of course, that's exactly what Frank Wenner was doing in the lab, which is why when he went out into the field, he recognized that if I just drive 2 pieces of steel into the ground and pass a current through them, I'm just mostly measuring the ground right next to the steel, the contact of the steel with the ground. I'm not measuring the resistivity of the ground. But if you make a measurement with 2 more electrodes, then you can make a proper measurement. So that's the basis of the DC resistivity method, and that's the last time I'm going to talk about that. So because if you've got a wet rock, and it's the ions in the rock that are doing the charge transport, when the ions get to the electrode, it's electrons in the electrodes that are doing the charge transport. And so you've got ion meets electron, and you can perhaps transfer charge a little bit. But basically, the ions can't go into the electric circuit, so they pile up at the ends of the rock. And that's called polarization. And what happens is it creates an electric field in the rock that's opposite to the electric field you're trying to pass through the rock. And as you make your measurement, your resistivity is just going up and up and up. It's not a realistic measurement anymore. It's called polarization. So you get around that by using an alternating current. So you keep reversing the direction of these charges at some high frequency so they don't pile up on the edges of the rock. So that's the trick. And you can get really clever with that by changing the frequency at which you make the measurement and sweep through a whole bunch of frequencies. And then you can discover that not only do you have a sort of a capacitor where the electrodes are, the resistance where the electrodes are, you've also got capacitance inside the sample and the resistance inside the sample. And by sweeping through frequencies and measuring the phase and amplitude, or the real and imaginary components, so this is just the in-phase resistance, and then this is the out-of-phase resistance, you get these semicircles, where each of these semicircles is associated with a resistor-capacitor couple in the sample. So you can use, this is called impedance spectroscopy, and people in the lab use it to pull apart the complicated way that electric current is traveling through this sample. This is called a cold-cold diagram. So the lowest frequency arc is associated with the actual rock itself, and these higher frequency arcs associated with the electrode surface. And so here's an example from some of my work. I mean, this is a complicated system of gas hydrate and seawater and sand, and the low frequencies are in blue, the high frequencies are in yellow, and you can see, so I misspoke. This is the high frequency arc, not the low frequency arc. And you can see how you're getting these arcs sometimes too. And these are what we call the equivalent circuits. So each of these blue lines is a mathematical model of a resistor-capacitor pair, or even 3 components or 4 components that will fit together this way. This is temperature on this axis here. So as the temperature changes, the conduction changes. We'll talk about that in the ability of the charge change. And this is the sort of geology changing from seawater to sand. So you can see how we use this method to pull apart the complications of the conduction. So water conductivity depends on temperature. This is the conductivity of seawater as a function of depth. As you go down in the ocean, it gets cold, and so the conductivity goes down as you For most things, when you make them hot, you increase the speed at which the charge carriers move, and so the conductivity goes up. So the ions in the ocean basically can move much more rapidly at the surface, where it's about 20 to 25 degrees C. The deepest ocean is about 3 degrees C. And so if this red line is the temperature and the blue line is the conductivity, and you can see they're related. To a good approximation, the conductivity of seawater is about 3 Siemens per meter plus the temperature in C on 10. So if the temperature is 0, it's about 3 Siemens per meter, and if the temperature is 20, it's about 5 Siemens per meter, which is almost exactly what we're seeing. And if you heat the seawater up even more, an interesting thing happens. In order to get it above the boiling point, you've got to put pressure on it. And as you really increase the temperature and pressure, the resistivity goes back down. So it's sort of complicated. And if I took seawater and cooked it up to about 300 degrees C, its conductivity will be about 10 times what I would get in the ocean. But that's all I can do. I can't make it even hotter and more conductive because then it starts to come back down again. And that's relevant because deep in the earth, the pressures are high enough that the water temperature can get above boiling. In fact, the temperature of the water coming out of volcanic systems on the seafloor in these so-called black smokers can be as much as 300 Celsius. Okay, so this is actually relevant to the real world. Okay, so I've got a rock and I've got some water, and I know the conductivity of the water. And the rock's made out of quartz, which I know is basically infinitely resistive. How do I model that? And the famous equation is called Archie's law. It's a simple power law. The conductivity of the rock is given by the conductivity of the fluid or water times the porosity to some power. And this power is usually about 2 in sedimentary rocks. So it's like porosity squared. And that's Archie's law, and to a good approximation, it works for sediments. You can get other mixing laws as well. This is a mixing law that's based on fluid-filled tubes, which you might get in some sort of volcanic systems. And then these things called the Hessian-Strickland bounds, which are the mathematically determined limits to conductivity in a two-phase system. And the HS lower bound is the most resistive you can make the rock for a given porosity. And it's associated with the conductors being little isolated grains. So there's no connection between these conductors. So you can have, as much as maybe half the rock made out of conductors, and you don't get much conductivity through the rock. And then the HS upper bound is fully interconnected conductors. And so anything you find in the real world has to lie between these upper and lower bounds. And Archie's law, which models sort of a plastic sediment, planes with water, or perhaps even melt, is in between. And in pictures it looks like that. So here's a sandstone. This is porosity going from nothing to 1. Let's assume that the water conductivity is about seawater, which is about 3 Siemens per meter or 0.30 meters. Archie's law is this red line here. The HS lower bound, the HS upper bound is down here. That's the most conductive you can make it. And the lower bound is up here. So these bounds aren't very useful. But if you've got a fluid system with maybe conductive minerals along with conductive water, these bounds narrow down. So this is a way you can, if I'm looking for groundwater, I measure the resistivity of the rock as being 100 meters, and I know the porosity is about 50%. I can use Archie's law to work out what the salinity of the water will be and decide whether or not it's drinkable. So this is useful stuff. It gets a bit complicated. Yes.
How do you determine the experiment you want to score? Because every time I've asked uncomfortable healthcare, everybody they see that these kind of makes sense.
Yeah, well, I know Amazon very well. That's what we do. So there are two ways. The first way is if you're a petroleum geologist like Int'l working in a given sedimentary basin with lots of well logs, you take all the measurements of porosity in the well logs and the resistivity logs, and you plot everything out and work out what that experiment is for that given sedimentary basin, for that given rock type. If you don't have any information, the answer is two. Two works really well for almost everything and won't be very wrong. So I just use two unless I've got a petroleum geologist on the same. Two works. I mean, two works down to 1% crack porosity in granite. Archie's law works way better than you expect. So it's designed for sedimentary systems, but it actually works really well with igneous rocks as well. So yeah, two rocks. If you add clay minerals, things get complicated because clay minerals have got these dangling bonds that attract. Whoa! There's a button on here. Sorry about that. I should use the stick. Clay minerals have got these dangling bonds which sort of accumulate charges in the water, and they sort of locally change the electrical conductivity. So if you've got conductivity of the rock versus conductivity of the water, you get this linear relationship for high conductivity water. But then when the water conductivity goes to low, if you've got clay minerals, things level out because the clay is essentially making the water conductivity higher just because of these charges. And you can model that, and this is the math people use. It's a lot more complicated than Archie's law. And it's to do with this measure of how much clay charge you get. And it's sort of complicated. What you need to know is that if you add clay to a rock, you tend to make things more conductive than otherwise be complicated. So let's look at some of the math. Moving electric charge, the conductivity of a rock is given by the density of charges, the charge on the charge, which is using some fraction of an electron. It's either one electron or two electrons, depending on the valence of your ion. And then the mobility, mu. And the mobility is basically the velocity of the charge per electric field. And the drift velocity. And so we use this term drift velocity because the charges are bouncing around really fast inside. But when you put an electric field on, they move in the electric field, but they might be bouncing backwards and forwards at a much higher rate. And so Hawkins drift velocity. I'm running a little behind here, so let's move a little faster. So drift velocity is basically depending on the mean free time between collisions and the mass. And so you can write conductivity in terms of the mean free time between collisions. And for metals, it's the electrons, free electrons moving around. And when you heat a metal up, the mean free path goes down as the electrons move faster. And so in metals, when you heat them, the resistivity goes up, the conductivity goes down. For everything else in geology, it's the opposite. Semiconduction is when you have these conductors that get elevated into conduction bands. There are bona fide semiconductors in geology. This is iron pyrite, sulfide, iron sulfide. That's a semiconductor. You can get magnetite is a good conductor. You can get that in serpentinite. You can get, in theory, you can get carbon precipitated from CO2. So you get some specialized rocks, and especially ore minerals where you've got bona fide semiconduction. But the thing that's really interesting is point defect conduction in single crystals. So let's assume this is a crystal of salt, sodium chloride. And you think of sodium chloride as being conductive when you dissolve it. And if you've got a pure crystal of sodium chloride and no water, there are no ions, all the ions are covalently bound, ionically bound, and you're getting the charge movement. But you can create failures, defects. So I can move a cation into, put its place where it should be, into an interstitial space. And that's a moving charge, and that's called a Frankel defect. Or I can leave a hole where a cation should be, and that's called a Schottky defect. And the number of these defects goes up with temperature, and they go up exponentially with temperature with a Boltzmann relationship. And so that's the exponent of some activation energy divided by Boltzmann's constant times absolute temperature. So as you heat a crystal up, you create more defects as you increase the energy of the system. And these defects can move, and they can move under electric fields the same way chemicals move under diffusion in chemical gradients. I won't go into the details here. So this is a thing called the Nernst-Einstein equation, and it relates mobility of the defects to the diffusivity of the chemical gradients, and this is useful in predicting conductivity from diffusivity, which can be measured in other ways. The bottom line, from our point of view, is both the concentration of the defects and the mobility of the defects is exponential, thermally activated exponentials. And exponentials are very strong functions. And so everything else sort of becomes irrelevant except for this exponent. So the bottom line is, in these mineral systems under temperature, the conductivity is some constant times the exponent of an activation energy divided by K2. And you can linearize this, right? If you take the logarithm here as a function of 1 over t, you get a straight line. And that's exactly what you see. So here's a thing called cobalt olivine. This is reciprocal temperature, that's 1 over T in Kelvin. And these are the real temperatures up here, 600 to 1200 C. And then this is the logarithm of conductivity. And the data just form a lovely straight line according to this exponential, until some other exponent takes over. So here something has changed. Maybe the charge carrier has changed. And you might have several conduction mechanisms in a material, and then the exponent changes. And there's a little area where two exponents are working together, but because exponentials are such strong functions, one of them will soon take over. And this is called an Arrhenius plot, after Gustav Arrhenius, which was a famous chemist. So we can measure the conductivity of minerals at manifold pressures and temperatures by putting them in the laboratory. This is a piston cylinder apparatus, and you get an extra term in the exponential here under pressure. So you can basically put your sample in a small amount of material that transmits pressure, and then you put it under these anvils, and then you put these anvils in a big press the size of this room, and you can crush it up to manifold temperatures. And if you're clever, you can push wires in here to make the conductivity. If you want to go really deep in the earth, you use a diamond anvil cell. which is just pure magic as far as I'm concerned, because you take this tip of a gem quality diamond and flatten it, and you put your sample in some sort of deforming gasket, and you press two diamonds together in this press. And so these systems are only about that big. And you can wind up, you can just use a little hand pump on your bench and wind up the pressure to the bottom of the mantle. And if you're really clever, you can pull a couple of wires in here and make it. And people who do this are amazing as far as I'm concerned. But it's done all the time. You can even fire lasers in here to heat the sample up and then use X-rays to work out what the sample's doing because diamonds are transparent to light. Of course, if you make a mistake, you break the gem quality diamond. So why do we do that? Well, you know, as you go down into the mantle, interesting things happen. So here's the Earth. It's got this core, liquid iron, solid iron, you know all about that. And then you've got the mantle. The top part of the mantle here is a mixture of olivine and pyroxene and garnet, but you see it's mostly olivine. And so olivine is really important from my point of view. And then in the transition zone, the olivine goes to high pressure phases of olivine. So the atoms in the olivine rearrange themselves a little bit, but the chemistry doesn't change. So olivine goes to wosniite, and then it goes to ringwoodite, and the garnet and the pyroxene form a high pressure garnet called majorite. John Major was Ted Ringwood's technician, so he put his name on high pressure ringwood. Ted Ringwood was a famous geochemist that worked a lot of this stuff out. And then at 670 kilometers, the seismologists tell us the seismic velocity changes. And the reason it changes is because all of a sudden, this olivine garnet-based system completely rearranges the atoms. And all the iron, most of the iron and magnesium goes into this thing called magnesium-wustite, which is iron magnesium oxide. And all this silicate minerals go into this thing called silicate perovskite, which is now called ridgemite. So going down here, the olivine isn't changing chemistry, it's just rearranging crystal structure in the high pressure phases. And at 670, everybody shares every atom and rearranges themselves and creates a completely new mineral system. So there's a big deal. And seismologists see it, and it turns out the electrical conductivity goes up by a couple of orders of magnitude. So we see it too. So that's why it's important. So this is olivine, lovely green thing. It's an iron magnesium silicate. So it's a mixture of, it's mostly magnesium and silicate tetrahedra, iron magnesium silicate. But every now and then, in the mantle, about 10% of the magnesium is replaced by Fe2+. And the thing that makes olivine really interesting is iron is a really interesting material because it's very common throughout the solar system, and it can exist in two valence states. And it can exist as Fe2+ or Fe3+. And it's oxygen that makes the change, oxidation. So going from Fe2+ to Fe3+ is an oxidation process that releases electrons. So if I've got an Fe3+ sitting on a magnesium 2+ site, from a charge carrier point of view, that looks like a positive charge. So as I oxidize iron in olivine, I add oxygen, I create these Fe3+, and I also create some magnesium vacancies. And you already heard me talk about vacancies as Schottky defects that can transmit charge. But this charge on the iron can also jump from iron to iron and transmit charge as well. And that's a really strange conduction mechanism called polaron hopping. And it's really important in Earth because it turns out to be the dominant way olivine conducts charge, and it's probably the way perovskite conducts charge. Okay, so here's what it looks like. Here's forsterite, which is pure magnesium olivine. Then this is olivine, where some of the magnesium is replaced by iron, about 10%. And then I add oxygen, and I oxidize one of these ions to Fe3+, so it looks like a positive charge. And then this charge decides to hop over here. So that looks like a positive charge carrier in the crystal. And that oxidation created a magnesium vacancy, which can also move around and looks like negative charge carrier. So olivine conducts in two ways. At low temperatures, we have these polaron hopping between iron atoms, and at high temperatures, it's magnesium vacancies. And I wrote a paper with a colleague, Jeff Roberts, where we pulled this whole system apart with some laboratory measurements. And you can see as the temperature goes up, the red line is polarons and the blue line is magnesium vacancies. As you increase the temperature, the magnesium vacancies go up until at 1300 C they become equally important to the conduction. And so this is a mathematical model of olivine conductivity versus temperature, which is really useful if you're trying to work out what's going on with conductivity of a metal at a given temperature. And you can do this for all the other minerals. This is silicon perovskite. You can see that it's orders of magnitude more conductive than olivine. This is major iron here, and then this is magnesium-worstite, which is really conductive. But because it forms discrete crystals, it's a small fraction of the lower mantle, so it's the perovskite that determines the conductivity. Yes.
So about olivine, you say there is these two ways to conduct. Is that because it's a different type of olivine? And
No, this is the same olivine, it's just the temperature. So it's back to this picture here, that as the temperature goes up, you can suddenly end up with a different charge carrier. And that's exactly what happens in olivine. At low temperatures, it's this polaron hopping, and then at high temperatures, it becomes magnesium vacancy. The mobility of the magnesium vacancy with temperature goes up faster than the mobility of the polaron hopping. So the polaron hopping doesn't much care about temperature. It's just an electron hopping between iron. But to move a vacancy requires more energy. So it needs more, it works. So as you go up in temperature, so the magnesium vacancy is this blue curve. As you go up in temperature, you end up with the magnesium vacancies. And so this curve bends, this curve bends as you go up. So if you chase this exponential, so this is a log scale, right? If you chase that exponential down here, the magnesium conduction is small compared to the polaron conduction. And that's what you see in these pictures here when I'm working them apart. So they're both there all the time. It's just that because of the exponentials, only one dominates conduction. Does that work? Okay. And there's a few slides on the conductivity core. I won't go into the details except that we know it's really important. Conductivity of the core is really important for all sorts of reasons, including the formation of the inner core. And the early measurements on using shock waves were up here around 3 micrometers, but pretty well that's come down now, and the conductivity is about 10 to the 6 is zillions per meter or 1 micro. And that's been, the thermal conductivity and the electrical conductivity are related. So the electrical conductivity is an easier thing to measure, core pressures and temperatures than thermal conductivity. And so people are really, well, these people are not interested in induction. They're interested in how long it takes to form in the core. The conductivity can vary with direction. If you've got this is actually some olivine measurements. And these are the 3 crystal directions in olivine. So the conductivity is slightly different. But rocks in general can have conductivity that depends on direction. That's called anisotropy. And you can get it at the grain level, or you can get it at the sedimentation layering level. But the point is, from a electrical conductivity point of view, when you're measuring large pieces of the Earth, as you'll see, the EM method is fairly low resolution. So whether it's crystal level, grain level, or interbedding level, it all looks the same to measurement. Conductivity, generally speaking, is going to be higher in the horizontal direction than in the vertical direction, because these are working in parallel and these are working in series. The anisotropy can come through sort of rods or sheets, and depending on the particular magnitude of the conductivities in the configuration. Here's an actual result that we did some work off San Diego, so that's where I work, just here, and this is a couple hundred kilometers off. We made some EM measurements out here, and we came up with a model of the ocean crust where we can see the anisotropy associated with the dikes in the crust, and then we saw an anisotropy associated with mineral alignment that looked like rods in the mountain. That was a few experiments. Okay. So now some math. So any questions about mineral conductivity, rock conductivity before we do some math? Who likes math? This is Carl Friedrich Gauss. This is Gauss's law. So there's 2 forms of these Maxwell's equations. There's the integral form and the differential form. The differential form is the way to go to do the theory. The nice thing about the integral form is it tells you what the physics is doing. So the integral form of Gauss's law says that if I integrate the electric field over a surface, taking the normal component, it's equal to the charge enclosed by that surface divided by the permittivity, right? So if I've got a charge, I draw a surface over it, I integrate the normal component of the electric field, that tells me how much charge is in it. That's Gauss's law. Okay, so all the electric field leaving a volume is proportional to the enclosed charge. Faraday's law, if I integrate the electric field along a circuit, that's equal to the negative time rate of change of the magnetic flux. Right? Okay. So if I've got a changing magnetic field and I take a circle around it, then the electric field around that circle is defined by Faraday's law. Gauss has a law for magnetism as well. He basically says if you integrate the magnetic field over a surface, it gets 0. And that's another way of saying what goes in must come out. Or there are no magnetic molecules. You can't have the magnetic equivalent of the charge. Why is that? It's okay if you don't know the answer, because there are people out there who are still looking for more. But I think the real answer is magnetic field is not an intrinsic particle problem. Mass, charge, they're intrinsic properties of particles. There's no monopole because the magnetic field is not an intrinsic particle, intrinsic property of a particle. Magnetic field is a property of moving charges. And if you really get interested in it, you can actually describe the mathematics of the magnetic field as relativity associated with moving charges. And that's in the back of a famous book on the end theory. It's complicated, but you know, where does the magnetic field come from? We've been studying magnetic fields now for 4 days. Can anybody tell me, why you have magnetic fields?
Moving charges.
Moving charges, yeah. Why does a moving charge create a magnetic field? I should. What is it? So it's probably relative. But anyway, that's an interesting thing. So that's why there are no monopoles. Ampere's law says that if I integrate a magnetic field around a circle, it's the current passing through it. So if I've got a wire with a current, and I draw a close loop around the wire and I integrate the magnetic field, I can work out what the current is. Okay. So these are what the differential form of Gauss's 2 laws and Ampere's and Faraday's law are what we call Maxwell's equations, except there's this thing that's so incorrect. That extra term in Ampere's law that Maxwell added allows magnetic fields to exist without electric current, or even without charges. This is the permittivity of that. And this is a little bit of magic that allows an electric and magnetic field to exist in a vacuum in a way that creates light propagating. And the speed of light is 1 over mu naught epsilon mu. So that's really what Maxwell did. And we're not going to have frequencies and conductivities that make this term significant. So from that point of view, we use Maxwell's equations, but not really. We're just using Ampere's law and in matter, as opposed to vacuums, you have different permittivity and permeability, which means that you have magnetic dipoles are lining up in a magnetic field, or you've got a little charge separation in an electric field, and this causes polarization and magnetization. You've been studying magnetization, so I won't go into any details except that for us, we don't really have enough magnetizing rocks to affect the induction, so we're going to ignore all this too. This is important. This is Ohm's law, which relates moving charges in an electric field. It's called a law, but these are all approximations. The polarization or the electric current doesn't have to be linear. Okay. Think of a diode. It's a conduct electricity in one direction but not another. That's not a linear system. You can saturate the magnetization in a rock. So you've probably seen hysteresis curves, right?
Yes.
Yeah, well, that's because you can saturate the magnetization in the rock, and that's not linear anymore. So these are linear approximations that are useful, but they're only approximations. So here's, you've seen this, right? This is Maxwell's statue in Edinburgh, and Maxwell's equations are enshrined on a plaque and this is the differential form in matter. So now we've got the displacement current instead of electric field. Except that these are all the heavy side equations. These are Maxwell's equations. He used quaternions, which is a really complicated way of doing things. All of the Heaviside spent years working out what all this meant and produced the equations that we use today. So what's going on here in electromagnetic induction? So I start out with a time-varying magnetic field. I've got a magnetic field oscillating at some frequency. That's our primary magnetic field. Faraday's law says that I'm going to get a circulating electric field. Ohm's law says that if I'm in a conductor, that circulating electric field is going to create an electric current. And then Ampere's law says that electric current is going to make another magnetic field. So this is back to the picture I showed you right at the beginning, where I've got a secondary magnetic field. And the minus sign in Faraday's law means that that secondary magnetic field is going to try and oppose the variations in the primary magnetic field. That's sometimes called Lenz's law, but frankly it's just so this means that as I wave a magnetic field across a conductor, it's going to get attenuated, and over distance in a uniform conductor, that attenuation is another exponential, where the length scale of that exponential is called the spin depth. And it's given by 2 over the angular frequency times the permeability times conductivity. Or in other units, it's the resistivity times the variance divided by time times the time conductivity. So, spin effect. Okay. So this is a Tesla coil. This is a thing that makes very high voltage radio frequency electricity. And the fun thing is you can draw sparks. Has anybody ever done that? Video out, people can do that nowadays. Just your video. Yeah, well, when I was a physics student, we had open house in physics, and I got the job of showing off the Tesla coil. So I got to draw sparks and wave fluorescent tubes around the globe. And I remembered that. I came up with this picture on the web. This is 1931, so I think they've stopped people doing it. And I was told that the reason it doesn't kill you is the frequency is high enough, the skin depth is shallow enough that the electricity flows over the surface of your body and doesn't get in and kill you. Okay? It's a lie. You work out what the skin depth in human flesh is, we're about the same conductivity as seawater, which some people use as an indication that we sort of evolved from fish. So, if you work out what the skin depth is in people, it's about 25 centimeters of radio frequency, which is enough to get into your heart. It turns out that radio frequency doesn't hurt the nervous system. So it's not the skin depth at all, it's just the frequency. But that's probably why they don't let people do this anymore, because it's not a good idea. So let's derive the skin depth equation. Here's Ohm's law, and here's Ampere's law. So if I substitute the J for sigma E, I get this. And then I'm going to take the curl of that. So I take the curl of both sides. And then I know that Faraday's law says the curl of E is minus the dBt. So I can substitute the dBt in here. And then I use a vector identity that says the curl of A is the gradient of the divergence of A minus del squared A to get this. I substitute this. And then Gauss's no monopoles law says that the divergence of B is 0. So this becomes del squared B is equal to mu naught conductivity times the time derivative of B. That is a diffusion equation. That's the same as a heat flow equation. Okay. I can do the same thing for E. Okay, and I can substitute the curl of Faraday's law into ohm and ampere of the curl of Faraday's law. And I get this curl equation again. But before I can do the vector identity trick, I need the equivalent of the known monopoles law of conductivity, and that doesn't exist. Okay. So what I have to do is to use this vector identity on Ampere's law, which basically says that the divergence of J is 0. And what I have to do now is to say that for constant conductivity, this is the same as the divergence of E being 0. So for constant conductivity, so conductivity changes, the divergence of E can be something. But for uniform conductivity, the divergence of E is 0, and then I can do the same thing as I did before. So up until this point, everything was general. But from now on, I invoke constant conductivity. That's what we call a half space in geophysics. Up here I've got the air with conductivity 0, and down here I've got an earth with the conductivity is constant. Now that's not real, but it's useful. And so now I've got the same equation in E as I had in D. Right? So these are the two diffusion equations describing electromagnetism. Why do we do this? Because Ampere's law and Faraday's law all relate E and B, but now I've got equations that have only E or only B, and they describe electromagnetic diffusion. And here's what that looks like. If I've got a pulse of electromagnetic, if I've got a pulse of magnetic field propagating with time in the Earth, it diffuses down just like heat flow. But you might say, okay, heat flow, that's about the most useless geophysical tool there is. Why is EM induction any better? And the answer is we get to play with frequency. We can change the scale length by changing the spin depth, by changing the frequency. And this is where EM induction sits in the geophysical hierarchy. Up here we've got the wave equation, which is what Maxwell created for wave propagation in a vacuum. And if we have ground penetrating radar, the frequencies are high enough that this second derivative term here is significant. And so this is the radar equation where I've got the diffusion equation plus the displacement current term here. And that's exactly the same as the seismic equation with attenuation. So radar looks like seismic. Then the frequencies that I'm using for induction and the conductivities that I'm using, this term goes away. And that's because the electrical conductivities we're using are order 1, but permittivities are order 10 to the minus 10. So this frequency has to be very, very high before this permittivity term is equal to the conductivity term. So here, this is the heat flow equation as I advertised, and our the resolution of the wave equation is proportional to the wavelength. So if you send a seismic wave through the Earth and get it out the other side, it records information along its path in proportion to its wavelength. And that's why the seismologists can look at small bumps and we call that the boundary. The diffusion equation, our resolution depends on how deep something is buried. So if I bury a 1 meter diameter chunk of iron about a meter deep, it's very easy for a metal detector to find that. If I bury a 1 meter chunk of iron a kilometer deep, I can never see it. So our resolution depends on size and depth. But it gets worse. If I go to zero frequency, this term goes away, and I'm left with Laplace's equation, which is the gravity magnetism equation. And I can say this in public, but there's no resolution in zero frequency gravity magnetism. You can only talk about bounds on depths, bounds on size. That's very poor resolution. You can explain any given gravity observation with a near surface variation in depth. So has no depth resolution. But we have depth resolution for the skin. So now it's time to consider a single frequency. So I'm going to use the Eulerian way of describing frequency, saying that the magnetic field varies in time as b to the I omega t, where I is the square root of -1, omega is frequency and t is time. So now my dB dt just becomes I omega b. And so our diffusion equations become these equations because I'm just replacing the dB with I omega b. And then if you look at this gradient term here, if the magnetic field at the surface of the Earth is horizontal and uniform, which is a good approximation to the magnetospheric fields, these first two terms in the gradient are zero because there is no x and y gradient in B. So I just have a vertical derivative of B is equal to I omega B of z. So this is my half space again. So I can take I omega mu naught sigma conductivity, and I'm going to call that k squared, where k is this complex plane number. So now my equation is dB, the second derivative of b with respect to z is equal to k squared times b of z. And that's a second order linear differential equation that has a solution of the form of this, C1 e to the kz, C2 e to the minus kz. This first term is going to grow with depth, which is clearly rubbish. So C1 must be 0. And if we put C equals 0 at the surface of the Earth, where I've defined B, we can work out that C2 is just the surface magnetic field times e to the t. So from that, we have this term here. The magnetic field as a function of depth is the surface magnetic field times this exponential dependent on k. And we can rewrite that as the depth over z naught. The z naught is derived from k, and it's just 2 over omega mu naught. So this is our scheme. So this is what it looks like. The magnetic field falls off exponentially in skin depth, which means every skin depth is about 37% smaller. And the I here means the frequency, the phase changes linearly with depth with 1 radian every skin depth. So here are skin depths in typical materials. So at 1 hertz in seawater, the skin depth is about 290 meters. But 1 day in igneous rock is 50,000 kilometers. So this is how you can trade frequency and conductivity to get different skin depths. So we have access to skin depths at kilohertz in sediments. The skin depth is tens of meters. And if you look at daily variations in the Earth, we can see probably several hundred kilometers. So we derived the skin depth equation, which is not how you survive present. Okay, so
No, yes.
Taken by horse and cars along the road. Must be a local custom. Okay, yes.
Can I ask a question?
Of course.
Two questions. When you talk about the skin depth, and you showed the profile before bounce 1969 in the how do you call neutral net? Because one frequency is one speed depth.
Yes, so this only works in half spaces, which is why I kept wanting to show this picture here, the reminder that this only works in uniform. So all of this math, when I got to this step, conductivity had to be uniform. So you can define skin depth within a uniform conductor, but when conductivity is changing, there's a different skin depth in every bit of the structure. And things get really complicated, and after lunch I'll tell you how to solve that problem.
So one frequency is sufficient to make it define?
No, no. No, because one frequency, you can always describe it as a half space. So you need more than one frequency with different skin depths in order to get the depth structure.
And the second question regarding the situation, because it can separate the magnetic field and the electric field, but in the device, in the magnetic field system, you are measuring actually the electric field and the magnetic field. So according to these equations, they are all related to the same sigma. So is there some redundancy in these measurements?
No, because there's no way here. I mean, I'm using the magnetic field at the surface of the Earth and a knowledge of the conductivity and frequency to tell you what this magnetic field is a function of depth. The measurement of the surface of the Earth doesn't tell you what's going on inside the Earth. For that, I need to know the conductivity and know the frequency. So the measurement of the magnetic field doesn't tell you anything about what's happening inside the Earth. If I measure the electric field as well, then I get to this. Okay?
But from space, you can rely on magnetic fields only. But you need to separate it from the response from the source.
That's right. You have to, we'll talk about that as geomagnetic depth sounding. For that, you need to assume a geometry. And again, a single frequency is not enough. Okay. So, the magnetospheric method. This is somebody else's slide. I didn't do it. So we've already talked about this, where we make time series measurements, we process them up into these data as a function of period, and turn that into a resistive model. So this is sort of what it looks like in practice. There's Peter Scher digging a hole for a magnetometer to bury it. We'll explain why you have to bury the magnetometers when we talk about instruments. This is Jared Peacock setting up a recording system to measure the fields onto a memory. And then there are some electrode wires you can barely see running about 50 meters off into the distance. There's an electrode buried in the earth. So setting up an empty method. So this is the picture I showed you before, the logging system, induction coils, electrodes. So we just showed that the magnetic field as a function of depth is given by this skin depth equation here. We also know that the curl of B is proportional to the electric field through the conductivity. So if I consider B in one direction only, let's say I'm looking at this induction coil here, Bx, and if I look at the curl operator, this is what the curl operator looks like, the only non-zero component is this one, Bx because there is no dy. I'm only looking at the bx component, so these two go to 0, and these two go to 0. And if I'm saying that b is uniform, the y derivative of b is also 0. So this is the only term here. So I can write e, and this is the y component. This is the x component, y component, z component. So the only term in the curl is the y component of e. And so that's just equal to 1 over sigma mu d z, this term here. And I can get the dz from here by differentiating this guy. So I end up with the y electric field is the complex wave number k divided by quantity times the x. And I could do that again for the y induction and work out that the y magnetic field creates an x electric field with the same relationship here, but no minus sign. These equations are valid anywhere in the half space, but I'm really only interested in where I'm making the measurements, where z equals 0. So I have these two equations here, and k here contains my frequency as well as the conductivity comes through both k and 0. So these equations tell me that a y magnetic field is going to induce an x electric field, and an x magnetic field is going to produce a minus ey field. So here's what this looks. So this the square root of I here creates a 45-degree phase shift between the electric and magnetic fields. So these are real measurements, and Ex here, the pink curve. Sorry, Ex is the light pink curve, and it looks the same as the y component of the magnetic field. So this equation here basically says Ex is the same as Dy. And if you look at these wiggles, you can convince yourself that these two curves just look the same. But the ratio of these two fields is going to be proportional to conductivity. In the other direction, there's antiphase. So this goes up, this goes down. Right? So the Ey is anticorrelated with Dx, and that's Niemegk's work. Pretty well all over. So if I take the ratio of E to B, I get, well, we always square this thing for, because of k being the square root. So, quick little bit of math, the ratio of V to B squared is given by the frequency over conductivity. So I can rearrange this for resistivity, and basically the resistivity of the Earth is 1 over frequency times the ratios of the fields squared. And the phase between E and B can also be measured. So this goes back to this is a resistivity obtained from the amplitude, and then this is the phase difference. So I've got two measurements. And then the blue, the red and the green is the two different directions. So that's where the various components come from. And this is what Canyard published in 1953. Resistivity is 0.2 times the period of E over H squared, where these are in some given units. So this is still only true for half space, but we can compute this resistivity anyway and call it an apparent resistivity. The resistivity the Earth appears to have. And it's useful because if you work in apparent resistivity, you don't have to worry about just how big the magnetic field was when you made the measurement. Because if you work in fields, you have to worry worried about how, whether you're making measurement during a storm or not. So, so the two components of the magnetic field are related to the two components of the electric field through this 2x2 complex matrix called the impedance matrix. Now, I like the magnetic field because it's what I measure. It's measuring nanoteslas, it's what I measure in the field. Unfortunately, the people who made this equation up like the magnetizing field. And there's nothing I can do about it. If I rewrite all the equations in P, the moment you open the textbook, you're going to be confused. So you just have to track the fact that the MT people like to use H here instead of B, and so the impedance matrix is all defined in terms of H, and so there's a mu naught flip from the top to the bottom. There's also another thing you can, instead of the impedance matrix, the other thing you can do is just to take the linear ratio and call it the impedance scale in minutes or inductance scale. Biot's, Peter Vidal, famous German induction guy, basically used this. And we'll see this later if we talk about really detail. Magnetotellurics, we've got the apparent resistivity given by the ratio of E to H and the phase, which is the phase difference between E and H. And of course, when you look at the phase difference, it doesn't matter what level of E is. So this impedance matrix, it's 2x2 because if you've got complicated Earth structure, you can in fact contribute to the X electric field with both HX and HY, but we'll see how that works in different dimensions. So here's a mathematically correct picture of what the electric and magnetic fields look like in our half space. So they're oscillating at some frequency. If you look carefully, you can see they're about 45 degrees out of phase. And this scale length here is given by the skin depth. And I like to remember it this way. It's about half a kilometer times the square root of resistivity times period. So here, if this is a half space, we compute the apparent resistivity at every frequency because it's a half space, it will be the same thing. So the apparent resistivity will be the true resistivity in the half space, and the phase will be 45 degrees. So no matter what frequency I use, I'll get the right resistivity because it's always a half space. Okay. Let's put some structure in. What happens now? Well, I'll put a conductive layer in here. So now the skin depth is much shorter and the energy decays very quickly in this layer. Right? Wow. It's changed the electric field at the surface. You see this electric field is just a little bigger. So now, as a function of frequency, things change. Near the surface, it looks like a half space. And the answer is the same as the surface level. And as I get to longer periods and I start to get energy propagating down into the conductor, the apparent resistivity changes. And if this is conductive, the apparent resistivity goes down towards the conductor. And then the phase changes from 45 degrees. And the general rule is if the conductivity, if the resistivity is going down, the phase goes up. That's the way it is. So this is the trick with magnetotellurics. When you put different conductivity structure down deep in the model, it changes the electric field measurement you measure the surface. And that's the magic. Okay. I can do it with the resistor. So now the skin depth is big in the resistor, and there's almost no attenuation of the electric field. But for complicated reasons, magnetic field has changed. Now the resistivity does the opposite thing. Long periods where I have energy propagating down into the resistor, the apparent resistivity goes up and the phase goes down. So that is how the Int'l method works. It's great time. Yes, do it. Yeah.
No.
Oh, that one. Oh, time series. Yes, this is minus sign. No minus sign. So the x component of the electric field is proportional to B, the y component is proportional to minus B. So this is the x component, and these wiggles here are the same. But in the y component, which is this one here, when this goes up, this goes down. So that minus sign comes from it basically is the minus sign of variables. Any other questions?
Maybe I can show some data. Maybe you can tell me.
Context concentrating on the deeper earth induction methods, but the main point I want to make is that the reason the control source methods proliferate is there are many combinations of measurement you can make. I've already said you can use either an inductive magnetic source or an inductive electric source, but you can also make the measurements either in the frequency domain and the time domain. For induction, you need a time-varying magnetic field. And we've talked about single frequencies where you have a sinusoidal signal and the secondary signals have a different amplitude and a different phase and a different direction. Another way you can do this is to use a time domain method where you change the magnetic field simply by switching it off. So you put a current in a transmitter coil, steady DC current, you turn it off very fast, and the magnetic field changes very rapidly from on to off. And that induces electric currents in the ground, which take some time to decay because they're diffusing away from the transmitter. And so the measurement of the induced currents, which could be made with electric field or with another coil, tell you about the electrical conductivity properties of the ground. And you can fly time domain measurements from helicopters, or you can put coils out on the ground, so on. So the reason CSEF methods get complicated is you can have a transmitter that's in the time or frequency domain. It can be inductive or galvanic, and then you have the earth response, and then you can either measure receive signal with inductive or without galvanic methods, and there are dozens and dozens of different proprietary control source systems available, but the physics is all the same. This is a variation of the first picture, which is my particular method, which is the marine method, where I tow a galvanic horizontal dipole transmitter, and then I use magnetic and electric field receivers on the seafloor that just look like magnetotelluric receivers, except now they're receiving the signal from the transmitter. So that's, just to let you know that control source methods exist. So we talked about half spaces. What happens when you start to get layered structure in the Earth? I showed you this picture before. Layering works quite well in the Earth because the big changes in conductivity are driven by changes in mineral physics, and that's driven by changes in pressure and temperature, which tends to be radial. So the radial structure of the Earth is basically a one-dimensional approximation. It even works in geology because a lot of sedimentary features are driven by gravity, and gravity only ever points down. The one-dimensional modeling can work quite well even on a local scale. So, so we've got a Earth now with a conductivity that varies just with depth. And that could be from geomagnetic depth sounding or apparent resistivity data. So what we want to do is predict the magnetotelluric or GDS data for a given one-dimensional conductivity structure. Once we can do that, we call that the forward model. Once we can predict the data from a model, then we can try and estimate the model from the data. That's the inverse method, and that's where I'm going to finish up today before I hand it over to Oliver for the practical. So there's two basic approaches to solving the electric and magnetic fields at the top of a stack of top of a one-dimensional Earth. You can solve the equations I've just shown you for a one-dimensional model numerically, or you can solve for a stack of layers where the conductivity is constant within a layer. That turns out to be a very efficient way of doing the one-dimensional model, and it's the way everybody does one-dimensional modeling. But I'm going to introduce you to the finite element and finite difference methods in one dimension, because when you go to 2 dimensions and 3 dimensions, that's the only way you can do it. So by introducing it in a simple case, I'm getting you ready to be able to do it in more complicated ways. So here's what we've got. We've got a magnetic field at the surface of the Earth, which is some constant times the sinusoidal function. And that's generating an electric field as a function of depth at the same frequency. So this is our magnetotelluric source field, and then this is what happens inside our one-dimensional Earth, and we want to be able to predict the electric field at the surface given the conductivity of depth from the magnetic field. So, go back to the math. We can combine Ohm's law and Ampere's law to get the curl of B as a function of E. We've seen this already. We can take the divergence now on both sides of this equation and then use a couple of vector identities. This thing is known to be 0 for all sensible fields A or B, and then this can be written as this is a divergence of a constant times a field, and so we have 0 is equal to the conductivity as a function of depth times the divergence of E times the divergence of the gradient of the conductivity with depth. we've already shown that this can go to 0, and because E is just horizontal and the gradients and conductivity are vertical, so our diffusion equation still holds. Now, last time for the electric field, to make the diffusion equation work, we had to show that divergence of E was 0 by keeping the conductivity constant. Now we're going to invoke the fact that the horizontal electric field times the vertical variations in conductivity are also 0, and that gets our diffusion equation back. So for a single frequency, our diffusion equation just becomes this, and for only vertical variations in the electric field, we end up with the second vertical derivative with respect to z of E is equal to Iomega times E is z times conductivity of z. So the problem here is, given a conductivity was a function of depth, find electric field everywhere, and then once we know electric field everywhere, we can work out what it is at the surface. We need a boundary condition to solve this, so we're going to say that at infinite depth, the conductivity is 0, because all we see from the skin depth that no matter what the skin depth is in any part of the model, eventually the electric field has to be far away. So for a single frequency, the dBt is just Iomega b, and so Faraday's law just becomes the curl of E is equal to Iomega b. So the magnetic field is just given by the curl of E. And if you look at what the curl term looks like, we're back to this trick where there's only one non-zero term in the curl of E, because we're only looking at EY, so the EX terms go to 0, and there's no variations in X or Y, so all these terms go to 0. So the only thing we're left with is the EY dz. So this is what we already saw, that the X-directed B this is in the X component. So the dx is equal to 1 over E times the vertical gradient of Y. So if we put we look at the surface condition where our magnetic field is B naught, we see that at the surface, the magnetic field is equal to the first vertical derivative of the electric field divided by Iomega. So if we can calculate the vertical derivative of the electric field at the surface, we basically have a relationship to B. So if we look at the admittance function, which is the ratio of E over B, we can substitute the first vertical derivative of E for B, and we end up with the electromagnetic impedance is just given by E over its vertical derivative. So now we've got rid of B, which is good, because B is always changing with the magnetosphere, and we don't really want to know about that. We just want to be able to know about E. So we can choose anything we want for B naught, so we can be tricky and choose B naught so that the first derivative is -1, which means then that the electric field at the surface is actually exactly the same as the admittance. So given some conductivity functions at depth, we need to solve this equation with these boundary conditions. So we can solve this numerically with the finite difference approach. Finite difference method is where you approximate a derivative by taking the difference between two electric fields at two different depths divided by the difference in depth. And so the first vertical derivative at any one of these white points is given by the electric field at point n plus 1 minus the electric field at point n divided by the distance between them. So I've drawn this horizontally, but it's really with depth. And we could calculate second derivatives by taking differences between first derivatives. So we can compute all the derivatives we want. This second derivative by just taking differences on these nodes. And you don't have to space these nodes equally, but it's usually easiest for coding to do that. So we rewrite our equation here. So this is, I've just taken this equation here, right? Second vertical derivative is equal to the conductivity times the electric field. And I've written that in terms of finite differences. So I've got the electric field at 3 nodes divided by the square of the node separation, minus the frequency times the conductivity times the electric field is equal to 0. And I can rearrange this in terms of the electric fields on the nodes. Our boundary condition just becomes the difference between the surface and the next electric field divided by dz is minus 1. That's one boundary condition we use. And we know that the electric field at the bottom of our model has to be 0. That's the other boundary condition. So this is just a linear system, Ax equal b, which we can solve by inverting A. And so if we write this complicated thing here as a single number f, then this system of linear equations in the matrix form, A here just looks like this. At the surface, we've got basically E1 minus E2 divided by delta Z is equal to minus 1. And then all these other terms are just this term equals 0, all the way down until the bottom term is our bottom boundary condition, where the bottom electric field is just equal to 0. Right? So I've taken my partial differential equation, I've approximated to the derivatives of finite differences, and I've populated all of this in one equation, one matrix, which I can just invert. MATLAB is just a backslash. You don't even have to know how to invert matrices. Okay, so that's how the finite difference method works, and it's relative. It's actually, this is a really easy homework to code up if you're looking for something to take away. And you'll notice that I've written this f isn't really a constant, right? Because it really depends on. I should have written this as fi. In fact, I've been a bit sloppy because for every depth you put in the conductivity at that node in this f here. Okay. And that's how you take a given conductivity model and you can predict the electric fields all through the model, and of course then the electric field at the surface tells us what our impedance is. So that's finite difference. Finite elements are a lot more complicated. I'm going to whip through it pretty quickly because I want to get onto the stack of layers. The way finite elements work is if I've got this equation with a second derivative in it, I basically create a weak formulation of integrating this equation over some test function v between 0 and 1. And you can see that if this is correct, then this is correct, right? And these test functions are designed so that they're between 0, they're 0 at 0 and 1. So when you integrate by parts, this term goes away, and then this weak formulation becomes this equation here. And then you divide your function up into linear piecewise functions, these are your finite elements, and then these are your test functions which go to 0. And so what you do is you basically represent your function by these basis function pyramids in this formula here. And then you basically have some unknown function and you have derivatives. And because these basis functions are analytical, you can actually calculate the derivatives you need. Instead of using finite differences, the derivatives become analytical from your basis functions. So your weak formulation now is the sum of all these little temp functions. And then the test functions you can use in the weak formulation are the same little temp functions. So you end up creating another linear system of equations where your individual matrix elements are these integrals over these analytical test functions which you can calculate, and you can solve this system for you. So you can apply this to 1DMT. There's our second order PDE. You can write it this way. You've already seen that. And then you create the weak form, and then you can do the integration by parts. And we start putting in our basis functions. And it gets really complicated, which is why everybody likes finite differences and finite elements. But finite elements have lots of real advantages. So what's really happening is that your one-dimensional connectivity model is basically being sampled linearly between nodes by these test functions. And so you can, this is just the linear system for our one-dimensional connectivity model. And it's complicated, but you can write everything out in terms of these analytical derivatives of the temp functions. So nobody solves the one-dimensional model with finite elements and finite differences, but you'll see that when you come to 2D and 3D, you have to do that. What everybody does for the one-dimensional models is the stack of layers. So here's my stack of layers, and this is pretty general because you can use as many layers as you want to approximate your conductivity profile as accurately as you want. There's no limit to the number of layers. Once you have the mathematics sorted out, you can put in 200 layers, 300 layers if you want to sample your model. Yeah?
I was just wondering if this finite elements, the way you present it, can it be switched to splines?
Yes, you don't have to use linear functions. You can use more complicated functions, but the method I just showed you looks simple compared to what happens once you start putting in quadratics or splines into the basis functions. But yes, people do that. People who want to spend their life writing computer code to solve problems will do that. And it's not clear. I have a good colleague, Chester Weiss, who does this for his living. And he did this in 3D EM, and he did the quadratics and discovered that it was no better than the linear function. So you have to be careful. Okay, so here we have a stack of layers. And what we have is depths at each of the layer interfaces. What we're going to want to use is the thicknesses of the layers and then the connectivity layers. So the connectivity is constant in each layer. It turns out you can solve this analytically. So way back before lunch, we showed that the solution to Maxwell's equations for a constant conductivity is this function here. Now, for a half space, we showed that C1 went to 0, but this is not necessarily the case within a given layer. And this is our complex wave number here. So within any layer where the conductivity is constant, the vertical electric field obeys this equation here. So we just need to find C1 and C2. So here's a trick. Don't ask me how somebody thought of this trick, but somebody did, and so I can use it. Instead of C1 and C2, we can write this as A cosh and B cosh. This works because sine h of x is equal to this thing here, and cos of h of x is equal to this thing here. And you can actually show that C1 is just A plus B divided by 2 using k is the n plus 1, and C2 is A minus B over the same thing. So this is just a rearranging of the constants, but it works for us. So we need the first derivative. We showed that our impedance was just the electric field over the first derivative. So we can differentiate this thing here analytically, because we know the derivatives of sine h and cos h. So we can calculate the electromagnetic inductance anywhere in our model by just taking E over the vertical derivative. So let's start at the bottom of this layer here. At the bottom of this layer here, the depth is Zn plus 1. So if this is layer 3, the bottom layer depth is Z4. So in this form, these are my formulas up here. So at the bottom of the layer, Z minus Cn plus 1 is 0, because Z is at the bottom of the layer. So these differences here will go to 0. Sine h of 0 is 0, and cos h of 0 is 1. So these equations collapse to A over K and B. Okay, so that's simple enough. Now, here's the thing, because the vertical electric fields have to be, because the horizontal electric fields have to be continuous, the emittance at the bottom, the C emittance at the bottom of this layer has to be the same as the emittance at the top of the next layer. So I called C at the bottom of layer N as Cn plus, and that's got to be equal to the emittance at the top of the next layer, Cn plus 1. So what's the emittance at the top of the layer? At the top of the layer, Z equals Zn. So I'm just looking at the top of the same layer here. So this Z minus Zn plus 1 becomes the negative thickness of the layer, right? And so knowing that sine of the negative number is the same as sine of the number, and cos of the negative number is equal to cos of the negative number, we can rewrite these equations as this, where now Z minus Cn plus 1 just becomes the layer thickness. Divide everything by B sine h, and I turn these coshes and sines into cotangents. And then we know that A over B divided by Kn is just the impedance of the next layer down. So we actually have a relationship for C at the top of any layer in terms of C at the top of the layer beneath it. Okay, that's a recurrence relationship. That means if I know what C is at the bottom of this stack, I can then propagate this equation all the way back up to the surface. And we know what C is at the top of a height space. And this works because at the top of any given layer, the impedance depends only on the layers underneath. So it's only looking down. So if you're down at the bottom of this stack of layers, you don't care about anything above you. You can work out what C is at the bottom. We've already solved that. That's just E over B. We have the half space solution down here. And then we can write C at the top of the next layer based on this solution. And then we can jump up to the next layer. We can go all the way to the surface where we can get C. And if we've got C, we've got resistivity, and we've also got phase because C is a complex number. So that's it. Solution for a layered Earth. And it's what you do is write a little computer code that loops over every layer, computing the impedance based on the impedance provided. And that's how everybody does it. So that's your formula. You can also, if you really, that gives you the impedance directly. If you actually want the fields, you can calculate them by choosing a magnetic field at the surface, and then you can solve the electric and magnetic fields at every layer. So Ulrich Schmucker did this. Ulrich Schmucker, a famous German EM person working out of Germany. And he created a formula for current resistivity that looks very similar to what I've just shown you. Pretty well everybody uses this one nowadays, and instead of computing the current resistivity, it gives you the impedance, empty impedance Z that we've been talking about so much. Again, all of these is you start at the bottom and you just work your way up to the top. So this is the 1D solution. Yeah, the spherical Earth is interesting. I've just shown you the flat Earth. The 1D spherical Earth, you can map a spherical geometry into a flat Earth geometry through this transformation by Peter Byler. That's how you can solve the 1D forward problem in different ways. Finite elements, finite differences, and a stack of layers. When you go to 2D and 3D models, there's no equivalent to the stack of layers. You have to solve it numerically using the finite differences and the finite element methods. And most people do this by creating the curl-curl equations in either electric fields or magnetic fields. So we've already done this for a given frequency. And what we've done is we've used a vector identity to turn this curl-curl into something simpler. But in 2D and 3D, you basically just leave it like that. You can solve the electric field everywhere in your model, and then you use Faraday's law to calculate the magnetic field. Well, you can solve the magnetic field if you want to, but nobody does. And you can introduce sources of currents, and if you want to control source, you can put in dipoles for currents or magnetic fields, or if you want to use magnetic tellurics, you put in uniform magnetic fields as the source. So this curl-curl equation looks like this, which, if you squint carefully, is just another AX equals B for some complicated system, linear system of equations. So to solve the forward problem in 2D or 3D, you basically have to do a large matrix inverse of the type that we did for 1D. There are some other tricks. If you've got a complicated source, sorry, if you've got a complicated model in a one-dimensional background, you can divide it into 2 bits. The one-dimensional background, which you've already solved for E and B in, and the difference. And then you can decompose this into background connectivity plus the 3-dimensional effects. And then you've got the electric fields can be written as the electric fields in your background, which you can do analytically, and then the complicated effects are solved numerically. And if you've got any complicated three-dimensional source terms, you can often bury that into the analytical part of the equation. So in 2 dimensions, your finite difference, instead of being a line, just becomes a grid of points, and you can calculate derivatives in any direction. In 3D, it becomes a mesh of points. In 1D, we kept the mesh spacing constant for convenience. In practice, in 3D, you want to start increasing the mesh spacing in the edges of the model, otherwise your model gets too big. But the problem with using a fixed mesh structure is that if you've got fine grids in the middle of the model, they tend to propagate out because you have to use more formula to set points. And then there are other tricks to compute the fields. You've got boundary conditions that you have to worry about. So the normal currents have to be continuous, and the parallel electric fields, the tangential electric fields have to be continuous. And the trick here is this staggered grid in the finite difference method, where you compute the magnetic and electric fields on the edges of these paddle wheels. This is the Yang grid. So you integrate. You take the circular electric field around here to get the magnetic field in the middle, and then you take the circular magnetic field around here to get the electric field along an edge. And this way you make the boundary conditions work. And at the end of the day, you're just creating another linear equation where you put all your conductivities and electric and magnetic field derivatives into this matrix here, solve for the electric fields on the edges of these cells, and all your conductivities are contained in this test here. So finite elements in 2D becomes a little more complicated. Your test functions now are these things over triangles. But unlike that regular mesh you saw for finite differences, with finite elements, you have the ability to change the mesh within the model and create complicated things. And in 3D, the triangles become tetrahedra, and your basis functions start to look really complicated. But there are people who do this, and there are computer codes that handle the tetrahedra. There's a code called TetGen, which is public domain, which allows you to build up these 3D models from the tetrahedra and then work out how to put all your finite element mathematics on top of it. If that sounds complicated, you can just go and buy a code from Constable, which will model anything in 3D using finite elements. And it's a very well-developed, sophisticated code with a nice user interface. And you can build your own partial differential equations into the code. This is obviously designed to solve elastic properties in some structural component of a machine. But if you put in Maxwell's equations, it will solve Maxwell's equations for you on a 3D model. People have done this. It's more efficient to write your EM codes from scratch, and there are many groups all around the world, including a very good group in Germany here, Klaus Spitzer and Freiburg, who spend their lives building 3D codes to predict apparent resistivities and phases at the top of two-dimensional and three-dimensional. So that's the forward model, which is complicated enough. Now I'm going to talk about inverse modeling. That's the last thing before we all get to look at some equipment. So, any questions about forward modeling before I talk about inverse modeling? No, getting tired. Okay. We need inversion in the induction. Not everybody needs inversion. If you're a seismologist doing seismic reflectivity, you can look at all these other reflections and paint your geology on top. That's yourself on the back, publish your paper and go home. If you're a magnetic anomaly person, you can do something similar. This is a magnetic anomaly map of South Australia. You can see the geology in the magnetic anomalies. It's all very pretty. And you can do some simple depth of magnetic placement calculations. But if this is your data, can you see a salt dome in there? There's a salt dome in there. Big body of salt, big resistive wall. But we need inversion to take stuff that looks like this. These are magnetotelluric resistivities and phases. These are controlled source electric field amplitude. We can take that and turn them into pictures like this. These are the pictures I showed you already. Where we're getting quite a lot of detail from the geology from the data. You know, the data looks like that. So it's magic. So this is the geophysical inversion algorithm, and it will take data that's been collected over some geological Earth and convert it into the model. There's a lot of other stuff that goes into these algorithms as well that can influence your model, and that's something to bear in mind. So what we've just talked about is forward modeling, where you have some model parameters, connectivities of your layers or your blocks or your voxels. Some information about frequencies and locations when you collect the data, and some mathematical function which may in fact be a big finite element inverse problem in itself that takes all these connectivities and maps them into predicted data. Data that somehow may be similar to the data you collect. So you can take some conductivity model, run that forward calculation that I talked about just recently, and predict the data that you actually see over that model. But what we'd really like to do is to take the data and find a model. Give them some observed data with errors, find a model. There's various ways of doing that. There's trial and error model. You can just, don't laugh, it's been done, I'll show you. You can think of a model based on what you know about the geology and predict the data and look at the differences between the data and the model and say, I don't think I'm going to change this color and do it all again. That used to be the only way you could do that. There's deterministic models based on Newton algorithms. There's stochastic modeling based on so-called Monte Carlo methods, genetic algorithms, simulated annealing. And then there's analytical. For some 1D problems, there are analytical inversions the same way as there's an analytical forward problem. But only for two problems that I know of, one-dimensional M2 and one-dimensional resistive. So this is a cover from the AGU's EOS magazine in 1988. This is the result of a magnetotelluric study across the longitudinal subduction, which you remember was in one of those 3D models that I showed you right at the beginning of today. This was done by Phil Wanamaker with trial and error. He basically built this model by looking at the data, building the model, running it, looking at it. And here's a picture of the data, and here's a picture of his model response. Not too bad. Why did he have to do this? Well, there were no 2D inversion algorithms available prior to 1990 when I was young. And this is 1988. There were no inversion algorithms. Trial and error forward modeling is all he had. And he did a pretty good job. Of course, he painted the subduction zone in because he expected to see one. So you never know when you do this how much is given by the data and how much is Phil Wanamaker's picture of the Earth. But still, it fits the data, so you've got the function. Stochastic methods are where you take a random or quasi-random bunch of models, you do the forward calculation for all of them, and you see which ones are close to the data you actually collect. It's useful because you only need to do forward calculations. It gives you some measure of uncertainty. You get a whole bunch of models which all fit the data, and you can look at how those models distribute in space statistically. But in practice, you have to create millions of forward calculations to do this, and so it really only works for simple 1D and maybe simple 2D problems. Then there's the deterministic algorithms that you guess a model, and then you update it until it fits the data using this thing called a Jacobian matrix. So this is a matrix of the derivative of every data with respect to every other model. So I've got a whole set of data. I've got maybe 1,000 connectivities in my model. This matrix tells me how every single data point changes when a single model connectivity changes. So it contains all the information about how the model changes the data. It's called a Jacobian matrix. It's a lovely thing. And then finally, there's for one EM induction problem, that's the 1D magnetotelluric problem. Bob Parker created an analytical solution to the inverse problem. Basically, he says, if you have some data, you feed it my algorithm, I'll give you the guaranteed least squares best fitting model. And it's formidably complicated mathematics. Continued fractions and all sorts of stuff. But you wrote a computer code and gave it away, so anybody can do this. There's only one problem. The model he gives you is delta functions of conductivity. Basically, the conductivity is either infinite or zero, except at these, they're infinite at these single points where the conductivity thickness is defined, but the conductivity isn't. But this is the best fitting model in a one-dimensional set for MT. It's infinitely rough conductivity. Right? These are the first derivative of conductivity. Generally speaking, it's even if you don't have this analytical solution, as you try and fit your data better and better, your models get rougher and rougher. That is the nature of the geophysics we do. These are smooth models in the background here, and as I try and fit the data better and better, the smooth models get pointier and pointier. They're trying to imitate this delta function model called B+. So generally speaking, the problem with least square solutions to EM induction problems is that they're going to be maximally rough. So you have to be There's a single solution for one BC theory. So, some other properties of the inverse problem in geophysics. Geophysical inversion is non-unique. For a given misfit to your data, there's an infinite number of models that will fit, or maybe no models at all. So basically, you've got two possible solutions to inverting your data. There's an infinite number of models that will do it, or maybe there are no models at all. So that's not very satisfactory, really. And this is also true of other things. This is a gravity, a given gravity profile. It can be fit by any number of models at all sorts of depths until you get to a maximum depth. And so this is model construction. And in an ideal world, you try and find some unique property of the model. And in gravity, you have that. The total mass of all these bodies has to be the same. So though you can have any number of models that fits gravity profile, the actual total amount of density anomaly is given by the gravity division. So geophysical inversion is also poorly constrained. If you change your fit to the data a little bit, you can change your models a lot. I mean, this is that picture I just showed you. As I'm trying to go from RMS 1.1, so I'm fitting the data to 1.1 error bars on average, to the least square solution, which fits every error bar to about 93%. I'm going from a relatively smooth model to one that's very, very rough. So how do we measure the fit to the data? How do we know a given model is compatible with our data or not? Well, most people use the venerable sum squared misfit, where you take your real data, your prediction from the model, from your forward solution, you divide it by the data error and square it. You sum all that up, and you get this sum squared misfit. And in matrix notation, I can write it like this, and this is going to be handy in a moment. So D is my vector of data, D hat is my vector of predicted data, and W is a diagonal matrix of 1 over the data errors. And then my sum squared misfit is just WD minus D squared, which is 2 more. And if the data errors are normally distributed, Gaussian, then sum squared misfit is actually chi-squared distributed with m minus n degrees of freedom, where m is the size of the data set and n is the size of the model. Least squares, so this thing goes up as a function of the number of data. So I like to use RMS misfit where I'll divide it by the number of data, take the square root. This basically root mean squared tells me on average how big my misfit is compared with my error box. So if you have more data than model and your data errors are Gaussian and independent and zero mean, then the least squares solution is actually a good estimate of the model. But the trouble with geophysics is we often have models that are bigger than our data sets, and our data errors are not always Gaussian and almost never independent. So to solve this in a least squares sense, you take the derivative of the misfit and then set it equal to 0, and then this gives you a linear system, which is this, where beta looks a little bit like your model misfit, and alpha looks like your decoded matrix, and n is a changing your model from a starting model n naught. So if we start with some starting model n naught, we predict the data from that, and we also calculate the derivatives of the data with respect to all the model parameters. We can work out how to update our model by inverting this input vertical matrix here and multiplying it by the data misfit. And this will work for a small number of layers, but large data set. But it isn't even defined if you've got more model parameters than data. This is very common in 2D and 3D. And we also know that the least squares solutions have got to try and look like D plus this thing here. So almost all inversion today uses this thing called regularization to try and stop the model getting rough, to try and force it away from the D plus type solutions by penalizing roughness in the model. And so this is our model misfit, data minus model response. And we add to it some measure of the model roughness through this single constant called the Lagrange modifier. So this is some matrix R is extracting roughness from the model. And so this is a one-dimensional model vector. A matrix R might look like this, where it's taking the difference between every two layers, 1 minus 1 minus. So it's basically measuring a sort of first difference approximation to the first derivative of the model. It measures the slope of the model and tries to, if you minimize this thing up here, you both minimize your misfit to the data, but you're also minimizing the cumulative first derivative of the model. Sort of extracting a slope to the model. This does great things. It stabilizes the inversion, so it means the inversion knows where it's going. It can create a single solution where we know that there are an infinite number of possible solutions. There's only one smoothest model, and it allows your model parameters to be more than your data measurements. And this is a simple one-dimensional picture, but this is easily extended to 2D and 3D, where you take measurements between pixels in every direction. So this is the basic regularization approach. You've got this equation here with a trade-off parameter mu. If mu is small, say mu is 0, this just goes to the least squares solution, where you just make your model as rough as you can and fit the data. If mu is large, we ignore the data and make our model look smooth, and the trick is to find mu just right. Some people just choose a mu and then minimize this equation. I like to be a little more strategic about it. I basically, I think I know my data. I think I know my data error bars, and I think I should be able to fit my data to about one standard error. So instead of minimizing the misfit to the data and pushing all the noise into model roughness, we can step back a little bit and say, okay, I want to fit my data just good enough. I don't want to push it to a least square solution. I want to find a misfit that's equal to some number, roughly equal to RMS1, that's good enough for me. I can say I fit my data if I'm just going to a regular error bar on average. And then I make my model as smooth as possible. And that's the thing that I introduced with Kathy and Bob Parker a long time ago called Occam's inversion. And it's pretty well, one way or another, it's what almost everybody does. That's the basic Occam equation. F of n is nonlinear, so we'll bring in our good friend the Jacobian matrix and linearize around some starting model. So f of some new model n is f of the starting model plus some unknown step, which is approximately equal to the forward function of the starting model plus the Jacobian times the model step. derivative matrix I told you about. So we substitute this in for f of m up here, and we get this guy here, differentiate and set the thing to 0, and we've got something interesting. The previous least squares solution I showed you gave you a delta m as a solution. This approach gives you the next model as a solution. It turns out what that means in practice is that you can take big jumps in model space rather than just little delta m jumps. You notice that my target misfit has disappeared from this because it's a constant, and when you differentiate, it goes 0. So the trick here is to find this number mu so that the misfit is equal to the one you want. And that's the basis of Occam inversion. So Occam is a two-step process. You start with a model, and I start with a model usually that's got no structure to it at all, and I'll explain why in a moment. And then you do an iteration and you search over this misfit trade-off parameter, the Lagrange multiplier, and you find the one that gives you the minimum misfit solution. And you keep doing this until you hit your desired solution, and then you end up with two solutions, two models that will fit the data to the level you want. And you choose the one with the bigger Lagrange multiplier because that's the smoother model. And that's the basis. And then the nice thing about this is that you can keep going with the iterations, but nothing's changing because it converges to a solution. So that's where the stability comes in. So what's this doing in the pictures? Let's say I've got a simple two-parameter problem, and so this is one parameter, this is another parameter. The smoothest models are where the parameters are equal to each other. So that's where the roughness is 0, parameter 1 equals parameter 2. There's my least square solution, the blue dot. And then this surface here is my area of acceptable solutions, the one that's giving me Pascal star. I start here and I drive the solution down towards the least square solution until I hit my target misfit. And then I keep going, and the model gets smoother and closer to the smoothest model until it gets to the smoothest point on this surface. And then it just doesn't go anywhere. It converges, which is nice. So let's go back to this set of data that I showed you. This is magnetotelluric and controlled source data over a salt cone in the Gulf of Mexico. So they're two different data sets, but they're both sensitive to conductivity, so I can mix them together. And then I start with a featureless seafloor. This is the red is seawater, the blue is air, so they're fixed. They're not part of my model. I know what they are. This is a two-dimensional model. And this is my iteration number, and this is my misfit up here. I've split the controlled source and empty apart, but just look at the combined misfit. And then this is model roughness, which is down to 0 because this model has got no features at all. So the overall misfit is 9 error bars on average. And the roughness is 0. This is where I'm starting. I take one iteration. And the inversion algorithm drives the resistivity down. It changes the resistivity of the background and drives the misfit down to 5. But it doesn't actually add hardly any structure at all. It's basically just trying to fit the data a little better. Then it starts to put structure in, to drive the misfit down, and it starts to put roughness in. And then by iteration 3, I've just about hit my target misfit. My target misfit is about 2.4. explain why I've chosen 2.4 and not 1 and this. And so I put a lot of structure in here to fit the data, so my roughness has gone right up. But now, when I keep going, my misfit is staying constant, and I'm starting to make the model smooth, and the roughness is coming down. And I do that again, and then I finally have taken out all the roughness I can. My misfit isn't changing here, and now nothing is pretty well happening. I can march along for as long as I want and nothing changes. So this algorithm doesn't really care when you stop, as long as you get to this part of the curve. Okay, why do I start from the start of a half space? Well, the reason I start from a half space is because the Jacobian matrix for a nonlinear problem like Int'l induction depends on the model. So if I want to point myself, the Jacobian matrix's job is to point your inversion in the right direction. So I don't want to prejudice that by having a Jacobian matrix that's got structure in the beginning. I told this to my student David Meyer once. He went and did this little model here. This is an MT model with a resistor in it. What do you remember about MT resistors? It's not very sensitive to it. In 2D, you can see a little bit of it in TMO. So he did this, and lo and behold, no problem. The inversion algorithm took the resistor and moved it right where it should be. There's no harm done. The reason there's no harm done is the Jacobian matrix, because the MT isn't sensitive to resistors, the Jacobian matrix is small inside the resistor. He brought this to me and said, look, you're wrong, Steve, not a problem. And I said, you silly person, you shouldn't use the conductor. So he did the same thing for conductor, and guess what? The Jacobian matrix is huge inside this conductor, and so it doesn't point you in the right direction, and it just gets stuck. So that's why I like to start conversions without any structure in them. So choosing the misfit is sometimes subjective. If you've got good data errors and your model really is 2D, and you've coded it up properly, then maybe RMS1 is good. But often you don't. Often your model isn't two-dimensional or your data errors aren't well estimated. And so here are models with RMS 2.4, which is the one we just saw, converge. I can drive this all the way down to nearly RMS1, but look, I'm starting to get my rough model back, my D plus type model. So I don't know, maybe RMS 1.7 is good. This blue thing is the resistive salt thing. So sometimes it's difficult to know just how well to fit the data. What I like to do is to drive an inversion down to as small a number as possible and then back off a little bit. This tells me how good my error estimates are in my model parameterization, and then I can say, okay, well, I don't want a least square solution. I like something that's a little smoother. You've got to be very careful about data outliers, because the sum squared misfit measure is very unforgiving of outliers. This little data point here, which is clearly an outlier, if my error bars were 5%, that data point would have the same contribution to my sum squared misfit as 40,000 other data. Okay, so if I leave that in, and I've only got 200 other data, the model's just going to spend all its time trying to fit this. So you need to get rid of that, either by getting rid of it or changing its error bar to reflect the misfit. So the first thing you should do when you're inverting your data is to go try and invert it, and then go look at your misfits and make sure you don't have anything more than about 3 standard errors in them. Do something about it. It's also good to look at how your misfit is data set. So here's a 2D inversion, and if you remember there were TE and TM modes, and if you recall, I pointed out that the TE mode is assuming there's no conductivity variations along stripe, and the TM mode expects conductivity variations, but you can put that into the model. And so it's not unusual for 2D models for the TE mode to have bigger error bar, to be misfit more than the TM mode, because the model can put in surface variations to fit the TM data, but it can't put in along stripe variations to fit the TE data. So this is a measure of the model, not really doing 2D. But you can also look at it by frequency. This is the long periods are being misfit more than the short periods here. You can also look at it by site to see, yeah, this site out here is not being fit very well. So this is all, and you can look at the difference between phase and resistivity. So your error bars between resistivity and phase should be proportional. Remember I told you in 1D you can predict the phase from the resistivity. They're basically telling you the same thing. But you've got to make sure your error bars are appropriate sizes in phase and resistivity. One of the nice things about Gary Abert's NT processing code is it does give you good error bars. I tested this. Another trick is to use what's called a dual grid. So you're trying to solve your forward problem using some finite element or finite difference model discretization. The model you're inverting for doesn't have to be that fine. So you can make your model parameters bigger than your forward calculation finite element or finite discretation. And that's called a dual grid. So you could, in this case down here, I made the model parameters big, and there are maybe 4 or 8 forward calculation nodes inside each of them. You've got to balance your roughness measure in the horizontal and vertical directions. In this case here, this is a little synthetic study done by another one of my students, Brent. And with the default roughness measure, you've got an artifact because the horizontal roughness was being penalized more than the vertical roughness. And so this blob here created a fault where it really should be causing a blob. And you can make it cause the blob by weighting the roughness measure by the size of the parameters. Now this might look sort of obvious, but there was a time when the academic community's favorite inversion code produced this sort of effect by default. The default parameterization for the roughness measure created these things here, and everybody was finding faults. There's a very good 3D inversion code called ModEM. It's distributed by Gary Abert's group. It's the only easily obtainable public domain 3D MT inversion package. But one of the things it does is it regularizes not just the roughness of the model, but also the difference from the starting model. And so you have to be very careful. These are 3 models that fit the data, all with different starting models. This is something from Henry Grasser's group from Berlin, presented at an induction workshop a few years ago. So if your code does this, you have to be careful. You have to be using a reasonable background resistivity to make it work. You have to worry about the errors you put on your data. You have to worry about your regularizations. You have to worry about how you parameterize the model. And if you have prior constraints, such as the starting models, these all go into your inversion and determine what sort of model you get. And that's it. That's all you ever need to know, perhaps more than you wanted to know, about EM induction. As I say, it's a lot of stuff. The slide deck's pretty comprehensive. The notes I handed out are not perfect. Please don't pretend they're a finished product. They're sort of a mix of my lecture notes from several courses given over several years. Cover most of the stuff in this course. So if you ever end up looking at MT data, wondering what it's for, about, just go back to this stuff and refresh yourselves. And if you ever want to ask me questions, you know where to find me. I've got my email on the front page. And always happy to help students. So I will open it up for questions and see if I have some tea. And then we come back here at 4 o'clock because I think Oliver wants to show you a few slides about the instrument facility before we go down and look at the equipment. And I heard a rumor he'd actually set up an MT site for us. Or we could just take right now. Do you have any announcements?
Yeah, I would have. So if there's any questions, I would already like to give you now maybe the certifications that you were attending the IAGA school, and I don't think you're disappearing right now. I've already did.
Right, you've gone through the hard part, now you deserve your certificate.
Maybe you come in the front and then I'll tell everyone's name, and they're ending up receiving them, and then we have the public breaks.
Do you want? Yeah.